right, so good morning or good afternoon, everyone, depending on where you're at. So we're very excited today to have Corinna Brungs here for our last joint VMOL mzmine seminar. So hopefully you guys and you ladies have enjoyed this seminar series. I know I have. So yeah, for the last one, we have Corinna here. Now she received her PhD in Munster, and this was in analytical chemistry. I think this was where she was doing some work on tattoo ink pigments. So this is very, very cool. This was what I first learned about Corinna. Then she moved to do a postdoc at IOCB in Prague with Tomáš Fuskal, and he is one of the main developers of mzmine. And so there she also did lots to improve mzmine, and she efficiently generated many open MS libraries. She'll be discussing some of that today. And now it's very exciting. She just started a new position as the director of the MS core at University of Vienna. So congrats to you. And we're very excited to hear about the work you've been doing and that you continue to do. So with that, I will let Corinna take the stage.
Thanks, Allegra. Also, welcome from my side. And as Allegra already said, I will talk about the library generation workflow. But before I start and we dive deeper into the topic, just a recap, there were already 3 other sessions. So it's like from VMOL organized. So again, big thanks to all VMOL organizers. So to Daniel, Allegra, and Ming. And then it's in collaboration with the mzio team. And if you missed one lecture, they will be uploaded, or they are uploaded on YouTube, and feel free to check them out again. There will be also more series happening, especially from VMOL. They will also invite multiple different topics, so also feel free to still sign up. So it's for the VMOL session, so you will be informed if there's new topics showing up. And with this, Allegra already said what was my background, but here I wanted to show that I actually started more as a power user. So at one day we started to say, oh, actually we are not developers, we are not doing the coding, but that was happening with Daniel. So we said, oh yeah, we are the power users. So we use the software and we check what is happening. And if there's a bug, we actually, we make an issue or we speak with the developers what is happening. So as you already heard, I did my PhD in analytical chemistry on tattoo pigments, and I already used mzmine too. So this was the start where I actually got in contact with mzmine. So I used it to create a pigment library. I already used it for imaging data. So that was also the start to have imaging data kind of included, and also to have the IMS support. So I used the timstorflex in my PhD. So there was also the need for me to use or to have a software capable of processing IMS data. And that was great to have Robin and Steffen involved to ask, I need something, can you help me with it? So that's how I started. Then during my postdoc, I started with the more open spectral library generation, and there I started using then mzmine 3. So I actually moved forward to the newer version. Of course, it's always a hassle if you need to change software, or not the software, but if you need to change the versions. But it's actually good to change. So if anyone is still using mzmine 2, maybe think about moving on, because actually there's more happening in the development, bug fixing, and also including new modules and features. So I used mzmine 3 and mzmine 4 for this. So we included in mzmine the automatic library building workflow. And there was always in close contact with Robin to build like an actually automatic library building workflow. I also started during this time with programming. So I haven't touched any code before, and I was always like, yeah, maybe I will start and doing it later. But it's actually super nice to start programming. You know more about how software actually works. And then at one point I also started to add small own modules, or I did some minor changes in the code because I had something that was missing or something that I wanted to highlight or add. And we also started to do or to give more workshops on mzmine, and especially for me on the library building workflow. And now I started as a senior scientist at the University of Vienna. And of course, now I'm heavily involved in mzmine. I will use it as a processing workflow and also get in contact with more analytical questions and how we can solve it. And also, of course, maybe using other software tools as well, because I mean, there are many around, and this is just one option that you can use. So now I will start with the library building workflow, and this is all done at IUCB Prague. But since the library building, and I will talk more about it later, is a very important topic, so I still would like to be involved, or I'm still involved in the project, still at the University of Vienna. So if anyone is interested, you can always reach out to Tomasz or to me, and then we can talk about the library building workflow. And what you can see here already from the title is that we had like 38,000 compounds, and we managed to acquire them in a high throughput method, and I will go later through it, in 11.5 days, and this was for one polarity. So in the end, we used like 23 days to acquire those data, which is not a lot if we think about how many compounds we can actually push in the public domain. And the very special topic here is also that we have MSn, so we don't stop at MS2, so we actually do multi-stage fragmentation to get more fragmentation information from the structures itself. And just as a very quick recap, what is actually important or how is the workflow happening? So first of all, you normally have a study design, so it doesn't matter which sample type you introduce. Then you need to do your data acquisition to think about which ions is important for me. Is it positive mode, negative ionization mode? Which instrument is capable of detecting my compound? Is it electrospray ionization and so on? So there are many things to actually think about in the before starting with the experiment. And then if you have the data, you need to first analyze which signals might be important for your study. And then if you find some signals that are important because maybe they are upregulated or downregulated, and then you want to annotate those. So we need to be kind of detectives to actually annotate or identify what is the compound. And this is very much the problem what we now have, because if you think of an untargeted workflow, you don't know what you're looking at, and annotating compounds just by spectral library matching maybe doesn't give you the answer in the end. And I will also show why maybe the library matching is still limited nowadays, and that's why we need to work on it. And speaking about libraries, there are of course different reasons why you want to build this library. So the first thing, what most people do in their labs, if you have reference standards in your institute, in your lab, you normally, and especially from the compounds you're interested in, so you would use those standards to run the same LC-MS method to then use it as a proof that this is the compound you're searching. You have the retention time, you have the fragmentation spectrum. So this would be the easy way or the normal way how you start. So you have the standards, you run it, you want to have it as a library that you can then use in your group. Or maybe that is also important. Maybe you see something very often in your analysis, so it might be something that is unknown, but you want to have it in your library and then use it later on for other untargeted studies. Or maybe you see it very often already in every sample, so maybe it's some contamination from your plasticware. So this might be also interesting to have in a library. Maybe you annotate first your feature table with this spectra, or with this library, and then you would exclude them from the whole processing later on because they are not interesting for you, or they are not important for the study. And speaking about spectral libraries, and this is to highlight what we now have in the public domain, and I think it's already great because there are so many people involved that want to increase the public domain with spectral libraries. We have MassBank North America, MassBank EU as the first open library platforms. And then there was also GmbH, which was then formed to be more easy to upload data. So there's no strict rules how to upload the data. So that's why you can see they have already more compounds included, although they were established later than MassBank EU and MassBank North America. But because it's much easier to actually push the data which is also maybe something to highlight. If it's easy to publish, you sometimes don't know what is happening with the data. So there's sometimes profile data or centroiding data. So this is also something to keep in mind if you use any of those databases. If something is easy to upload, it's sometimes in the end hard to know what happened with the data or what is actually uploaded. But it's so great because we see that the number of compounds can be easily increased if it's like easier for people to upload the data. And then we can download from those databases, we can actually download the spectra, and then we can use it to use it in other software tools, or maybe to use it as machine learning training data sets and so on. So it's very easy or very nice to have the option to download the data. And then if we go to MZ Cloud and NIST 2023, those are also very big spectral libraries, but they are only usable in their own software. So if we think about we want to use it as training data set, there's no option to download the data and use it later on for other tool development. Because if you think about untargeted workflows, you want to find something that is maybe unique and of course can't be included in a database. But if you would only rely on spectral library matching, you will not get any information or any annotation just based on the library matching itself. So that's why it's important to use it for in silico prediction tools and so on. So that's why it's also important to actually increase the database, not only for library matching, but also for the future. And so the first thing I want to highlight, so when I say, oh, we have so little compounds included in the spectral libraries, what is actually, if we buy compound libraries, we acquire the data, and then we match it actually against, like what I did here, against GmbH or any open library, and actually see how many spectra can be annotated. So what you can see here is, like, I call it molecular universe. So I use the t-SNE visualization. So each node is one MSn spectrum, and then they are scattered around. And if they have a similar fragmentation pattern, they are close to each other. And then if a node or if a spectrum has an annotation, it's actually then highlighted in magenta. And we see here, we used like 49,000 MS2 spectra, and only 14% got an annotation rate. And those are compounds that you can easily buy, or easily, I mean, they are normally very expensive, but these are compounds you can buy from a company, and then you could acquire the data, and that's what we did, but still only 14% were included, or at least the similar spectra were included in the biggest open library in GmbH. So we see there's actually more work we can do as a community. And even if we zoom further inside, what is also very important, if we use molecular networking, we can then see that specific clusters are highly covered by spectral databases. So if we take the beta blockers, for example, we see it's in magenta, so it's the same. If it got a hit in the GmbH library, we highlighted it in magenta. And then we see that the beta blocker are highly covered in GmbH. If we go to sartanes, then it's like, yeah, more or less. So we get a hint. So what is also important here, in our case, we acquired standards. So we actually know which compound is behind each node. And then here we see now, if it would be untargeted, we would have a guess because we have 3 annotations. So it might be sartanes in our compound or in our MSn spectrum here. And then we have the cephalosporins, which has no annotation at all. So if you think about untargeted, maybe you would be like, oh, that's super interesting. So I should focus on this molecular network because it's highly unknown. But in this case, it would be only highly unknown because the data are actually missing in the public database. And so we see we can actually push more data out. So you would get more information and you could pinpoint to something that is more interesting maybe for your study, and it's not time consuming in the end. So if you think you would isolate something and then find out, oh, it's nothing new, then of course you maybe wasted kind of your time. And then, yeah, so with this, if you know it's like already included somewhere or it's similar to something known, then maybe you would not focus on it in the later experiments. And this is also something that I always want to highlight. It's a worldwide effort. So we have mass spectrometry worldwide in different fields, like there's no limitation. So we even have mass spec in space. And I think if anyone is interested in collaborating or has data already acquired, you can always, feel free to reach out to us, and we are happy to maybe include your data and to speak more about the library generation and how you can actually help and to contribute. And this is also when we come actually now to the mass spectral library generation in mzmine. So it's the easy way, or the nice visualization in an easy way. So we have our metadata so that we know in which injection we have the compounds. Then we acquire our data, we combine everything together in mzmine, we do the data processing, and then we annotate it based on the metadata, and then we export it as different formats, depending what you like, or if you want to use it later on in a different software, maybe you need a specific data format. And there's also the option to export different information. So of course, if you do LC-MS, you can export the retention time. If you have IMS, there's also the option to export the mobility. And if you acquire MS2 or MSn, of course, we export the spectral library, the spectral data as well. So there's actually, yeah, kind of no limitation what to export. And of course, this was just the easy way. So it's actually more work that is happening in the back. And of course, you don't need to do every step how we did it. It's just how our MSn library building was actually set up. So what we see is that we have 3 different parts that we need to cover. And I will also speak about it in more details. But if you want to know more about it, there's also the preprint out. And yeah, feel free to go to this page if you want to know more, or maybe you missed something, and then you can actually know more because it's explained in more details, and you can read it there. So the first part is the metadata cleanup, because what we found out is that if you buy compounds from the company, you get maybe the compounds as a tartrate salt or as different salt forms. And of course, if you do mass spectrometry, we will not see the exact mass with the salt. So we first need to remove the salts. Then we also introduce like a standardization so that we always have the same kind of smiles representation. And then we should get like the salt-free form with adding or removing the hydrogen. And then the exact mass is calculated based on this cleaned structure. If you also think about that you have maybe metadata and you only have the compound name, or maybe you only have the structure. So there's also in Python, so it's a script written in Python. So you can also query pubchem by name or by structure, and then you can fill out all missing parts in your metadata sheet. And depends what is your study design or what you're interested. We also implemented like Lotus search to see where the structure or compound was maybe already found or isolated. Then if you're interested in drugs, we also have like the information from DrugBank. Of course, you only can query DrugBank if you have access to it, or Campbell or Broad Institute to then flag compounds if they are already used in any clinical phase or any clinical trial. There's also a Python script, but this is so far it's very thermo-specific. It's like creating automatically the sequence for the data acquisition, because in my case, we had like 9,000 injections. So you definitely don't want to do it by hand. So that's why we also have this script written. So this was all written in Python, and you can also change it. And if you want to add something more, it's like, it's like open source, and you can change, download it, and edit and change parts as you like. The next step is, of course, the lab work. So what we did, we normally had like an automation to mix multiple compounds in one well. We normally set up to 10 standards is a good way, at least for our flow injection method. If you think, of course, about LC-MS, maybe there's also the option to mix more compounds, because then you actually save time per sample. In our case, we always had 10 standards in one well. And then we developed this flow injection data-dependent high-resolution MSn method, which was basically 3 minutes per sample. So it was very high throughput. And now maybe you're wondering about the flow profile. So in our case, we acquired MSn trees. And to acquire a full MSn tree, we needed at maximum 13 seconds per sample or per MSn tree. And that's why we needed to have like a wide elution profile of the compounds. And that's why we set up this dual pump flow injection to actually have like 90 seconds to acquire MSn tree for each compound, maybe for multiple adducts in the sample. And then depends on the preference that we set, how many ions or how many precursors you want to pick and how deep you want to go in the tree. So in our case, we went to MS5. And the next step is then the data processing in mzmine, which I will also show later on in the demo. And what is important and what you maybe already saw in the lectures before, we first, of course, need to do the data import, the mass detection to say, and the noise cutoff. And then the next step is actually the feature list building. In our case, because there was no LC-MS, we have this MSn tree builder. So also if you use flow injection or direct injection, this is the tool to choose, because then you actually extract the features from your experiment, and then you merge all corresponding fragmentation spectra on this one feature. And it doesn't matter if you do MSn or MS2, you can use it there. But if you use LC-MS, of course, then you would do the chromatogram building and the whole workflow that you saw before. And I will also show it later in the wizard, so it's pretty easy to set it up there. The next step is then the local database search, and this is what I showed before with the part A, basically. So this is the metadata that we just cleaned previously. And we basically search only the 10 compounds that we have in one specific injection. So we are not including all compounds for the search, because then we would annotate everything in a wrong way. So we really only search the 10 compounds, set up specific adducts, and then we only search those compounds with the mass in the corresponding data file. And then we also, because we do it in an automatic way, so we want to be sure we export something meaningful. So we have a precursor purity check, explained intensities, and also merging, and then we export everything. And I spoke fast about the quality checks because I actually want to highlight what is happening in mzmine. You will not see it, but you will later see it in the export of the library files, because every check and what was the score and result is then exported together with the library data. So the first checkup is that we check the precursor purity. So we actually go back for the whole MSn tree. We go back to the MS1 scan before triggering the tree and after. And then we see if we have something very high abundant in this isolation window next to the signal that we are interested in. If this is the case, we can flag it or we can remove it. And if you flag it, it's actually then highlighted later in the library, so you can later on then still remove it. And this is also the workflow we normally highlight, because it's better to keep it in your data or in the library, but it's highlighted as chimeric. And it's better than to remove it, because then it's gone and we lose the information that we got with this spectrum. So it's better to just flag it and keep it. And of course, if it's clean, this is the easy way, of course, then it's good. Then we also have the subformula notation. So with the metadata, we know what is the chemical formula that we have. And then based on removing carbon, hydrogen, nitrogen, we see if we can explain the fragment signals. So for example, if we have 3 times the loss of water, then we can explain the signal. And this is then also exported in the files itself. So we have it as explained intensity or in explained signals. Of course, the most abundant signals should be explained by a subformula. If something is smaller, for example, in the right panel, and we cannot annotate it, maybe it's some noise that we didn't remove, or but then it's not so important and maybe valuable for the fragment spectrum itself. The next thing we also do, because during the library building, optimization, and building up, we thought about what do we do if we have multiple times the same energy for the same precursor? Do we want to export it all the time, the same spectrum? Or what happened if we acquired it for multiple energies? So this is also what you can see in the picture here. So if we acquire for the precursor multiple times with the same energy, we export the best one, and then also a merged version from all same precursor, same energy. And if you have the same or different energies acquired for the same precursor, then we also merge this across energies to have it as a merged version. And this is also because if you think about, there's like stepped energy, for example, for thermo instruments. So there's already the option to actually set multiple energies during one run. And then you will only get a merged version of this spectrum. And if you would do library matching, of course, the matching or the score would be low, because normally the library spectra are acquired with one energy. So that's why we thought it's good to have it as a combined version, because there you actually add all the fragmentation information you get with like changing the energies, because maybe you shifted then to smaller fragments. So this is then stored in a merged version. And the merge is also like named then in the library itself. So you can in the end see what happened with this spectrum. Is it a merged one? Is it a single best one? Or what actually is it? And also what we also included is like a pseudo MS2 spectrum. So we actually merged the whole MSn tree and we combine it to one spectrum as well. Maybe there's only software that can handle MS2 data, so you can actually use those information. And of course, with triggering like MSn, we have on the full tree, you get more fragmentation information. And we think it's good to also have this combined in one file or in one spectrum that you can then also use to actually represent the fragmentation of one compound. And this might be also interesting for the future because there's more fragmentation development. How can we actually make it better? Because now with collision-induced dissociation, we are kind of limited in which fragments we actually get. So the annotation or the confidence in annotation might be a bit more limited because you can have similar fragmentation of different compounds. So there's also now electron-activated dissociation, which seems to produce different fragments or more specific ones. So maybe with merging the whole tree to one is more comparable in the end with different fragmentation mechanisms in the future. So this is all the merging. And then if you do the processing, this is what happens during the processing. So you get like the feature table. And then with the compound database search on the right, you then get the metadata annotation. So we get the compound name, we see which adduct type was matching based on the mass, and we also see what was the formula and so on. And maybe you're wondering now about the peak shape. So this is just the peak shape because of the flow injection that you saw before with the 90 seconds elution profile. So that's why it's so wide. So yeah, it's not a wrong like feature extraction. That is because of the flow injection method that we used. And then something also to highlight, and which is also interesting for people with LC-MS experiments. So there's the column fragment scans. And here you can actually see how many fragmentation experiments you have for this one feature. Because we do MSn, we have a lot. So you see for the upper ion, we have 134 fragmentation experiments. And this is, of course, we have different collision energies. We have MSn tree. We pick multiple precursors in each stage. So this is when you come up with like a lot of fragmentation scans. Normally, if you think about DDA and untargeted workflow, maybe you have around 2 or 3, depends. Or if you have like multiple experiments and the same compound over and over, of course, then you would trigger it multiple times, and then you would also see maybe a higher number if you have it in more samples. And this is how we can now come to the results of the library building. So we had like a lot of plates, a lot of 384 well plates, which was nice because you actually get a lot of compounds already with one plate injected. We had like, 23 days in the end. And this is the results we got. So before you saw, we had like 38,000 compounds included. But from this 38,000 compounds, we had already 4,000 duplicates. So that's why you see here 34,000 unique compounds. And then what is also important, we only managed to see 30,000 detected compounds. So again, 4,000, which you can also see in this in the left panel. We see that 4,400 compounds were not detected either in positive or in negative ionization mode. And what we can also see is that most ions were detected in both polarities, and then we have some that were only detected in positive and some only in negative. So this might be also highlighting if you sometimes don't see a compound, it might be because of the ionization technique. So if you use electrospray ionization, or maybe the polarity you choose for data acquisition. So sometimes it's important, or if you do untargeted, it might be worth to actually use positive and negative. And also, of course, some ions will be not ionizable in ESI mode. And for example, I also tested APCI with some compounds, and then we could detect like 25% more from the one that we didn't detect before. But this was just a quick check. So maybe from the 4,000, we would get more compounds in the database in the end if we would include different ionization techniques. And then we have here, because I also wanted to compare it with the other libraries. So we have Open, which is GMPS, MassBank EU, and MassBank of North America. And then mzcloud and NIST23 to actually compare which compounds are included in which database. And for this, we actually removed the stereochemistry. And then we see that NIST23, which is the newest version from NIST, they have a lot of compounds included. Now they have like almost 50,000 compounds, and 30,000 are unique, so they are not covered in any other database. If we go to our MSn lib, we already see that we get 21,000 or almost 22,000 unique compounds that are missing in all other databases. So we actually see if we would work all together, we could actually push this number of compounds and compounds that are missing in other databases a lot. So there's definitely something we can work together on it and make the libraries much, much bigger and maybe better from the quality. And this is then the updated table. So that's basically what you saw before in the figure, but just the numbers. So you see that we had like 30,000 unique compounds, and with MSn, we managed to create more than 2 million spectra that we already uploaded to Zenodo or GMPS. So if you're interested in using the data, definitely feel free to download them and use them. We have them exported as JSON format or MGF. And yeah, you can use them for your studies for annotation. And this is then the outlook, and then we will go to the live demo. So it's definitely important to increase the coverage of spectral libraries or coverage of compounds in spectral libraries. It's good for library matching, of course, because if you get a match, then you know, or you have a hint what the compound you're looking at might be. And of course, in the future, if you have something unknown, you will not get a hit. So we need to use the data for training in silico tools. So for example, Sirius or MS2Query. Nowadays, they normally use GMPS, but it would be good to actually improve and increase the coverage of compounds. So as I said, I also uploaded the data to GMPS, so they are also included there now. And then because we used MSn substructure prediction, we can now use this information as well to actually see how compounds might, or subparts of a compound might fragment. And this gives us more information about fragmentation pattern and mechanisms in the future. And again, it's a worldwide effort. So everyone interested, and I guess everyone using mass spectrometry has some reference standard in-house and acquiring the data for themselves. So definitely important to actually push it, if you can, to the public domain and make it accessible for other people to then use it for their library matching and tool training. And of course, this is all only done in collaboration with many people working on this topic. So we need to get compound libraries. They're normally expensive. So that's why I really want to highlight the help, first of all, of course, of Tomasz Pluska Lab for all the research. And then, of course, people who are volunteering to share their compound libraries, especially at IUCB, but also at the Institute of Microbiology in Prague. Of course, Danny, because he also had some very nice discussions with him, and Louis, and of course Steffen before he started at mzio, because we also had already a very good collaboration and discussion about the topic. And this is the end for the presentation. And now I can actually show you what we just what I just showed you before. I guess we can answer the questions after the live demo. I think there should be some time left. So the easiest way, if you want to start building your own library, is normally that you go from the wizard, because there actually everything is normally kind of set up, or in the end which modules you should use in which order. So it's way easier to use it this way. And then you have now here the option for flow injection, as we used in our case. If you use LC, then just use LC. And if you want to know how you need to set up everything, then it's definitely good to go back to the other presentations, like the first one or the second one. So the first one from Robin, or the second one from Ansgar, when he introduced different techniques, how you combine it and how you process it in mzmine and with the wizard. And then the only option is now that we need to change for library generation. It's actually the last, the last option here. So it's the parameter setting if you do DDA, DIA, or library generation. And then based on the library generation, you actually add this information here in the lower part of the wizard. And I already set up some, the workflow. It's not super important what I changed. It's just, and I will go through the most important steps. Of course, it's first you need to import the data, so where the path is. Then the flow injection, you see it has less options to set than if you do HPLC or UHPLC or GC. So this is not really important, to be honest. So it's just how many MS1 you see. And then the orbit setting is basically the normal setting that you also used for your LC-MS processing. And here I actually also used the defaults. And then the filters also not changing a lot. So the only important step is happening under annotation and library generation. So here's the part where we can add the metadata to our, for the processing and annotation. So this is the local compound database search. So you need to enable it, and then you go under show. So you need to have the path to your database file. So in my case, because it was the MedChem Express bioactive library, I cleaned it. So I used the metadata cleanup. And then, of course, the path where you can actually find it and the data format. And another option that you can set already during the wizard is the precursor MC. Do you want to calculate it from the neutral mass? So you have the neutral mass or maybe the structure information, and then you set up specific adducts that you want to enable in mzmine. Or you can actually already have like one line, maybe you see very different adducts, so maybe it's more important or maybe better for you to actually have already the precursor MZ calculated. So you can also use this with the as listed in database, but then you need to have a column that is actually defining this MZ value. The next very important step is the file name column. So this is for the library generation that you really only search the 10 compounds in the corresponding data file. You could either use the whole data file name, but then if you rerun the same compound or the same well, again, you would need a new metadata sheet or a need like column. So the easiest way would be to use only a substring from your library, and I can show it also later. And then you can add like the date or maybe the method as a prefix and suffix, but the same string part is always in the same file. It should be unique. And then you can also search this. So for example, you can say it library 1, well, or plate 1, well, A1, and then you use this as the substring you are searching. Then here with the column name, you can enable and disable whatever you have given in your database or in your metadata table. You can also change the naming from the column name, not from the mzmine data type. And then if you want to change it, you just need to press enter, otherwise you don't save it. And maybe another thing is that you always have to give a compound name so that actually you have some reference. You can also change it to Inchi key, for example. And then you would use the Inchi key as the compound name, but it's basically used as an identifier. And if you don't give it, or if you don't name it, then you would have an error during the processing. So that might be a reason if you don't come to the point or there's an error, then it's because the compound name is not given. And there's more information you can give during the library generation. And what is also newly added is that you can add the classifier or NP classifier. If you query it with your metadata and you have it as a column, you can now also import it and export it together in the library file as well. So this is the annotation. Then we have the library generation. Under metadata, you can say what was the library, if you upload it to massive Metabolomics Workbench or Metabolites. So you can add the dataset ID, where to find the raw data, then the instrument type and who acquired the data. And then the other important part is the export path, because you need to define where you want to store it and what is the name where you can, how to name it. And then with this, you can click create batch. You have everything that we set up. So you see it's much smaller from the batch when you generate it. So you only have the mass detection and then the MSn tree feature list builder. So that's what I said. If you have LC-MS, you would have the chromatogram building and smoothing and all those steps. But because we use flow injection, this is not important. And we only need to extract the features and have the corresponding tree merge to this feature. So this is done under this. And then the important step is the local compound database search. So we can go and already everything or almost everything is pre-filled. So we see that it's all set up through during the wizard setup. And the only thing that you still can change and that is not included during the wizard is the use adducts. So if you click on setups, you can actually select which adducts you see in your experiments. Do you see multimers? Do you see doubly charged or multiple charged ions? But be careful if you select multiple ions. Of course, if you have 10 compounds or maybe 20 compounds, there's always something if you select a lot of different combination that there's a lot of misannotation because of this. So in the beginning, if you go through it manually, you can definitely enable more adducts. But if you do the real export, I would focus on the most abundant one that you actually see very often. In our case, for example, we used the loss of water, M plus H, M plus ammonium, and M plus sodium. So there was no M plus potassium or multiple charged because we didn't want to include it. But for now, I will keep it as it is from the setup. And the other thing I want to highlight is this batch spectral library generation. Here you can actually set which MS data you want to export, only MS level 2 or MSn. It doesn't matter if you have only MS2, you can also use this setup. And what I want to highlight is the handle chimeric spectra and the quality parameters. So this is something it's also pre-filled by the default, but might be important or interesting for you to change during the library building. So you have the precursor MZ isolation tolerance. And here I actually would set the isolation window you used for the fragmentation experiments. So I used 1.2, so I would basically set it to 0.6 because the window is wider. So I want to include everything that might give a chimeric spectrum. And then we say what should be the purity, 75%. If I'm lower than 75%, I want to flag it or skip it. But for now, I would also say flag it because it's better to have it. And then the quality parameters is what I said with minimum explained signals or the intensity. So how many signals from the MSMS can we explain or we can explain with a sub-formula level. And then you can also, because every value is exported, so in the beginning, I would definitely say to not include it, because later on, if people want to have very high confidence spectra, then they can always filter for explained intensities above, I don't know, 80% maybe. So that's something you can still change after building. So I would normally select to export everything and then to filter later on. So this is the important, and then we also import the library as a quality parameter. And yeah, and we also search the own data against the spectral library. So it's just as a quick checkup. So you basically could remove all those steps later on because the only important part is happening during the batch spectral library generation. So I will hit start and then we already see how fast it actually is. We already export the library data. It's only 11 files, but still. So during the time it's exporting, we can open one feature list. Or maybe not. Yes, we can. And then we can sort for the annotation. And then we actually see what I just discussed or also showed already as a screenshot. We can see the compound database annotation, the adduct type was annotated. We can also see the structure. And then nowadays we can also see if we use classifier and NP classifier, we can actually see the annotation from those parts and we actually export it as well. So you have more compound class specific information now about the compound. And what was also very interesting, for example, here we have something that is annotated as a doubly charged. So this can be always checked. If we check the isotope pattern, then we should see something that has an isotope pattern not from C13.1 then, but with half, so 0.5, and this is actually the case. So there you can actually check if multiple charged is the correct one or if there's some misannotation. And then you can go through and see, yeah, what was the annotation, what is the adduct type we actually see, and so on. So this was the part. And then something I also want to highlight. So we now have the compound database annotation. And something I also faced during the MSn generation or data generation, there's no really good tool to actually visualize the MSn data. So this can be done with the MSn Spectra tree visualizer. And then you can see we have all MS2 precursors or MS1 precursor that were then used for fragmentation. And we see how often it was triggered for the tree. So here we see something that was very often triggered, and then you can click on it and you can actually see the whole tree in one visualization. So maybe I can make it a bit bigger. So in the first panel, we have the MS2 data, then MS3, MS4, and MS5, if we triggered till MS5. And then all the time we have different colors. It's just the colors are only corresponding for each panel, so you can't transfer the color from MS2 to MS3 or MS3 to MS4. So the colors are always just for each precursor in each stage. And then you can see which signal was corresponding to which color. So for example, if we look in this part, we see this was the precursor picked, and then everything that is yellow is then corresponding to this precursor. So it's a very nice overview to see if there are new signals or how rich your MSn spectra are, and see everything in one visualization without like clicking and changing all the time for different MSn level and so on. So it's a very nice, option. And then you can go through each feature or each precursor and see how rich the fragmentation actually is. So this time, again, we see also MS5, and sometimes here it's the case we only see MS4. And then there's also the option, because as I said, with the pseudo MS2 merging, so if you do two merged scans, only the upper part is not the important one. And then you see highlighted which signal was only coming from MS2 or which signal is new based on the MSn. So we would miss if we would not use the MSn fragmentation. So we see this signal is high abundance. So of course we see it already in the in MS2, but there are some smaller signals that we then only see, and it depends on the compound, and that we then only see in the fragmentation pattern. And I told you that we can also, do it for not only for flow injection, we can also do it for LC-MS data. So I have this prepared. I will not go through each step. It's basically, again, annotation and library generation, and everything else is depending on your setup. You can, again, click on create batch, but then I need to delete the libraries. And I can click OK. And then we already see it's, again, very fast. We export already, so we can already open one as an example. And here we see now it's the chromatographic peak shape that we expect with LC-MS. And then again, we get the annotation for the compound. What I want to highlight with LC-MS data is that we mark everything with the same MZ, with the same compound database entry, basically. So there's no way so far to actually say, oh, only use the most abundant ion or use this retention time range for this compound. So far there's, but this would be also hard if you would do it manually, because how would you decide manually which ion or which feature is the correct one? So for now, we export everything with the same MZ. So that's something to also be aware of. If you don't remove ions or remove features, you will annotate multiple ions with a different retention time, same MZ, and you will have it in the library. So that's something to be a bit more cautious about. And maybe also something to show is that there's, of course, the option to import libraries later on. So I can use this library. then you can normally, so that's what also already happened during the batch. So you can actually see how many spectra were exported. Here we see we have like 15,000. Of course, for the demo, I only use 10 files, so we will not have so many spectra. And then what we can do is we can convert this spectral library to feature lists, so we can actually do molecular networking with it. So we see it here, and then we can do molecular networking. I can use the control F and you type in networking, and then I already get the spectral molecular networking. I use the settings the predefined one, so I don't change it. And we see it's like for 15,000 spectra, or we already merged spectra from the same adduct and compound. So it might be less spectra. And then we can, again, control F, visualize. Better to type in network. You can also find it from the visualization, from the visualization tab here. And when we can open it. And then we see, of course, we have a lot of compounds. It's very complex. So and with the annotation. So here we have the big advantage. We actually know which compound we actually have behind each node. But if we would remove the annotation, I just need to find it. I need to click it to none. And then we actually see that it looks much nicer than with all the annotation included. And if I do it back to annotation, and then we can do the filter. It's just as an example, so I can type in sartane because I also already used it during the lecture. But maybe, of course, doesn't work as I want to have it. I want this one. And then we already see that the sartanes are again in one nice network. And if it would be something we don't know, but maybe we have just one annotation, then we actually would know much more about the compound and what it actually is. And so it gives you more information. But I think also during the seminar, the first day, Robin was showing more about molecular networking. And maybe I will not go into too many details, but it's also possible if you have the library data, you can import them, create a feature list, and then do molecular networking. And maybe I would use the networking now for the library as a sanity check, because then you can actually see, is the same compound class or similar class compounds merged in one network. And if not, maybe I would then also check what is happening. And so I think with this, we have a bit more time for questions, and I hope I didn't forget anything that I wanted to show. And I'm happy now to answer your questions if you have any.
All right, so thank you so much. That was a great and thorough presentation. And hopefully is of interest to lots of you. So why don't we give Corinna a round of applause. So thank you for sharing. And with that, we can turn off the video recording. And those of you that do have questions, please stay on and please raise your hand for the question and answer portion now.